So in this video, I'll talk about symmetrical components. What happens when the fault is not on phase A, rather on phase B or phase C in three-phase circuits. So let's just do a quick recap. So in the previous video we said, okay, phase A is faulted to ground. So we know phase B, phase C, we assume they will be zero, current. Then the zero sequence, positive, negative sequence currents will be equal in magnitude, and also they have zero phase shift. So say magnitude and phase shift. So if we do that, if we write the equations in a matrix format or matrix transformation, so phase A current B C is equal to matrix A, which is 1 1 1 A squared A 1 A squared. So A operator is just an angle of amplitude of 1, angle of 120 degrees. So I covered that in the previous videos, but that's just a reminder. Times the vector. So this is vector of phasor current. This is a matrix A, transformation matrix, and this is just the sequence components, the zero sequence, positive sequence, negative sequence currents. So if you write the terms for phase A current is just I0 plus I1 plus I2, which equals 3I0. Then if you want I0, it's just 1/3 of phase A current. And as I stated in the previous videos, we dropped subscript A because since we're talking about phase A, this is zero sequence of phase A basically, but we dropped it just to be simple. And we know since the zero sequence, positive, negative sequence currents are equal in magnitude and they have zero phase shift, so I0 is equal to I1 equal to I2. So that's why we said I0 is equal to 1/3 of phase A current. Now what happens if the fault is on phase B, to ground, not phase A? So we would assume phase A and phase C would be equal to 0. So if I do the same matrix as the previous slide here, so this is the vector of phase currents, phase A, phase B, phase C, matrix A. I'm not changing anything. So if I write, since phase B is the faulted, so I'm going to take phase B is equal to basically this row here. So it's 1 times I0 plus A squared times I1 plus A times I2. So that's what you see here. Again, A is amplitude of 1, angle of 120. If you take square, so it's just A times A, which is just 1 with an angle of 120 degrees times itself. 1 times 1 is just 1. 120 plus 120 is 240 degrees, or 1 with an angle of negative 120 degrees. It's the same. But anyway, so I get this, but you can notice here I have this operator here and I have this operator here, and I know this operator A squared, that means it's an angle of 240 degrees from here. So I1 of the positive sequence current is apart from the zero sequence current, if I draw the phasor diagram, by 240 degrees, and the negative sequence current is 120 degrees apart from the zero sequence. Well, we know that's not right. So in other words, we don't satisfy this equation here. The zero sequence current is not equal to the positive sequence current, is not equal to the negative sequence current. We know the phase that's faulted, those three quantities, they have to be equal in magnitude and they have a zero phase shift. So what's the deal here? because we know this is what we expected. There is no phase shift and they're equal in magnitude. So the issue here is because in the previous slide I put the same order here, phase A, B, C, but really you should start with the defaulted phase at the top, phase IB basically, but keep the same order. So I'm assuming ABC phase rotation counterclockwise. So in other words, A will go first, B second, then C third. Or if I start from B, so it will be B first, C, then A. So B, C, A, or A, B, C. So I have to keep that order. So I start with B phase, but I keep the same matrix A here, no change, and no change to the sequence current. So the only thing I need to change is start with the defaulted phase. So that's the, but keep the same phase of rotation. So now if I write the term out for phase B, so I have to use this row since IB is in the first row. So IB is equal to 1 times I0, which is this one here, plus 1 times I1, which is here, plus 1 times I2, which is here. So there is no phase shift basically. So then I0 is equal to I1 equal to I2, which is a third of the faulted phase. So now it makes sense. Now I can do the same thing for phase C if I have phase C to ground fault. So again, I just have to start with the faulted phase as the first, but keep in mind the same rotation because it's ABC. If I start from A, so I go A, B, C, go in this direction. Now if I start with B, so I'm starting with B here, so C, A. I'm keeping the same order. If I start with C, so it's going to be C, A, B, C, A, B. So I'm keeping the same order. This no change, this no change. Again, if I take the first row, IC is equal to 1 times I0 plus 1 times I1 plus 1 times I2. So in other words, I0 is equal to I1 equal to I2, which is 1/3 of IC. So that's something to remember, because typically in textbooks, we always assume when we talk about line to ground faults, we assume phase A is faulted to ground. We never talk about B or C faulting to ground. So it's just good to know how to kind of handle those cases. So that's all. Thank you and have a great day.